Welcome to 1 Minute Wonder. Today we discuss about Acrimsat. The Earth's weather and climate regime is determined by the total solar irradiance (TSI) and its interactions with the Earth's atmosphere, oceans and land masses. Evidence from both 34 years of direct satellite monitoring and historical proxy data leaves no doubt that solar luminosity in general, and TSI in particular, are intrinsically variable phenomena. Subtle variations of TSI resulting from periodic changes in the Earth's orbit, Milankovitch cycles, approximately 20, 40 and 100 years, cause climate change, ranging from major ice ages to the present interglacial, clearly demonstrating the dominance of TSI in climate change on long timescales. TSI monitoring, cosmogenic isotope analyses and correlative climate data indicate that variations of the TSI have been a significant climate forcing during the current interglacial period, the last approximately 10 years. Phenomenological analyses of satellite TSI monitoring results, TSI proxies during the past 400 years and the records of surface temperature show that TSI variation has been the dominant forcing for climate change during the industrial era. The periodic character of the TSI record indicates that solar forcing of climate change will likely be the dominant variable contributor to climate change in the future. A series of active cavity radiometers, ACRs, a new generation of sensors with the precision required for compiling a long-term TSI database for climate, were developed at the Jet Propulsion Laboratory (JPL) of the California Institute of Technology under the direction of ACRIM Principal Investigator, Dr. Richard C. Wilson. Their use in a series of active cavity radiometer irradiance monitor (ACRIM) spaceflight experiments has provided a precise and traceable component of the TSI database during more than 90% of its 34-year history. The ACRIM science team moved its operation to Columbia University in 1995 and then back to the Jet Propulsion Laboratory under contract in 2008. The ACRIM instrument team, directed by ACRIM SAT Program Manager Sandy Kwan, operates the ACRIM SAT satellite, a CRIM instrument, and ground telemetry instrumentation at JPL. A contiguous TSI database of satellite observations extends from late 1978 to the present, covering more than 3 solar magnetic cycles. It's comprised of the observations of 7 independent experiments: Nimbus 7, ERB1, SMM, a CRIM 12, ERBS, ERBE3, UARS, a CRIM 24, SOHO, VIRGO5, ACRIMS, AT, a CRIM 36 and Source TIM7. A composite database combining these results using overlapping, in-flight comparisons has begun to provide new insights into the variability of total solar irradiance and its implications for climate change. Monitoring TSI variability is clearly an important component of climate change research, particularly in the context of understanding the relative forcings of natural and anthropogenic processes. The requirements for a long-term climate TSI database can be inferred from a National Research Council study which concluded that gradual variations in solar luminosity of as little as 0.1% was the likely forcing for the Little Ice Age that persisted in varying degree from the late 14th to the mid-19th centuries. A centuries-long TSI database will have to be calibrated by either precision or accuracy to a small fraction of this value to be of use in assessing the magnitude of solar forcing. The current TSI database is shown in Figure 1. Instrumentation used in spaceflight TSI monitoring to date has utilized sensors operating at ambient temperature of approximately 20 C. They provide the only practicable satellite instrument technology presently available for extended flight experiments. The native scale on which the results of each experiment's TSI observations are reported, is based on the metrology of their individual cavity sensor properties in the International System of Units (SI). The de facto, redundant, overlap TSI monitoring approach that has provided a contiguous record since 1978 resulted from the deployment of multiple, overlapping TSI satellite experiments. The traceability of this database is at the mutual precision level of overlapping experiments. This is typically orders of magnitude smaller than the absolute uncertainty of observations in the